All right, in today's lesson, we're going to be talking about section 1.4, and this is going to go back to shifting, reflecting, and stretching of graphs. This is something that I certainly stressed quite a bit in my Algebra 1 and Algebra 2 classes. So hopefully your teachers did as well, and you're coming with all of this very well stuck in your brain. So to figure out if you're ready, the first thing we need to do is make sure we can graph our parent functions with zero effort whatsoever. And so I would like you to graph, and I'll slowly scroll so you can write them all down, and then pause and get those parent functions on paper. So we're going to do the linear. We've got absolute value of x. We've got square, cubed, square root, and we'll just stop with cube root for now. Okay. Go ahead and pause the video and get those on your paper with accuracy, please. All right, here we go. We're going to graph this. We know that y equals x is an odd function like we discussed, and it has a y-intercept of 0 and a slope of 1. And so we can be 100% accurate and detailed with our graph without making a table of values because we know the graph. We know the absolute value graph is the same thing, except the negative portion here is going to flip up and be positive. And so we've still got our linear. And again, if you forget any parent function, all you have to do is make a table of values. And as long as you're not making up stuff, then you get the correct answer. We know that the slope on this side is 1, and the slope on this side is -1. This, by the way, is a piecewise function. Like we could rewrite this as a piecewise. All right, x squared. I don't know how you were taught it. I certainly stress the following. We know that it started at 0, 0. And then I know that we go up 1 over 1, and it's always up odd numbers. So I go up 1, and then I'm going to go up 3. 1, 2, 3 over 1. Next one will be up 5 over 1, 7, 9, et cetera, et cetera. That is how I remember it. That's how I would encourage you to remember it. And the reason that I do it this way versus think about this point being 2, 4 and the next point being 3, 9 is because when I'm graphing, right, if I'm going from this point right here and then I'm going to go up to 3, 9, well, I'm already up at 1, 2, 3, 4. I don't want to count 4 again, right? I just want to get up to 9, which is how many more? 5 more. So I go up 1, up 3, up 5. And that's how I have that pattern memorized. X cubed is, we're going to be at 1, 1. And then I know the next point is 2 cubed, which is 8. So I'm at 2 and 8. 1, 2, 3, 5, 6, 7, 8. Oops, I'm off the page. Didn't get a big enough graph. And then I know at negative, I'm going to be negative of the same things. So the way I have that memorized is it's kind of a cross between just knowing it's at 2, 8, but then also realizing that I'm down here at 1 already. So then to get to 8, I'm going to go 7 more, right? So I remember it as 1 and 7. And then if I need more than that, then I'm just going to have to do the math and figure it out, right? I'm going to have to go to what? 327. So I have to go, however many more that is above 9. So 18 more or something like that. But that's pretty rare that it'll need to be that detailed. So 1, 7 is how I've got it memorized. And then if you know those two, then really these are just flip them around. It's the same thing. So I know this is a square root. That's now going to be that same parabola we just graphed, but on its side. So instead of going up the odds, I'm always going to go up 1 over 1, up 1 over 3, up 1 over 1, 2, 3, 4, 5. So it's still the 1, 3, 5. It's just turned on its side. We also don't have the bottom half because whenever we see a square root, we assume they just want the positive root, unless you're the one who had to put the square root down to solve a problem. So this is how we create functions with square roots, because if we always did positive and negative, then those aren't functions. Cube root, we don't have that problem because we don't have that symmetry issue with the parabola. So I know that it's 1 and 7, right? So up 1 over 1, up 1 over, now it's going to be 7 this way. 1, 2, 3, 4, 5, 6, 7. Same thing the other way. We should be, and we'll kind of talk about this more when we review these in more detail, but my graph here is actually not very good. This appears like it's kind of coming at a nice 45-degree angle. And when in reality, if you were zooming in on that spot, what you'd see is that as it comes in, it basically goes vertical and then comes out of it. So that looks a lot more like that. It's just usually we're a little bit lazy and we kind of fake it. Okay. So then today, I'm hoping you don't even need to watch this video. In fact, it's probably going to have 0 views. Uh, we are just going to kind of review what happens as we then manipulate our parent function. All right. So example 1, go ahead and graph the function on the plane. Start with the parent function, and then graph all versions of it that I've asked for, g, h, and j, on the same plane. All right. So here we go. I'm going to try to match the colors. So the parent function, we know up 1 over 1, 1, 2, 3, and then really I should probably give myself more room. 1, 2, 3, 4. So we'll put it right there. Same thing here. It really comes up almost vertical out of it and then starts a pretty hard turn. All right. So then what is negative f of x going to be? So that's saying take your f of x answers, which are the ones we just did, right? And now change them to their opposites. So that means I'm going to be flipping it over the axis. And so this would be the graph of negative f of x. Okay? That's how we should read this. This is the outputs of f of x, and I'm just saying, hey, make the outputs the opposite. So if they were negative, they'd go positive. If they were positive, they'd go negative. All right. Now, what do we get when we do f of negative x? So this is blue. So what is that saying? Now, instead of plugging in x values and getting my answer, it's saying we're going to plug in the opposite of those x values, and it's going to be equal to those. So what that's going to end up doing is instead of plugging in, right, this is saying now when I plug in, let's say -1, right? So if x is -1, now it's -1. So we're going to get the same answers at -1 that we got at +1. So in other words, having a negative on the inside is going to flip your graph. That's pretty bad, but you get the idea. It's going to flip it across the axis. And that should be familiar because that was the even function definition. So this black and this blue, if this was one function, this would be an even function because the opposite is true on both sides. And then a negative on the inside, that flipped it over here, and then a negative on the outside, that flipped it vertically. And so this last one, this green one, should look, that's gray. That's supposed to be green. Now we get this color here, or this shape here. Okay, so the negative on the inside flips it one way, the negative on the outside flips it another way. And, if you didn't know all of that, a table of values would easily confirm it. Okay, so last thing I'd like to do before I move off of this is probably something I should have started with, and this is my bad. I should have probably written what the equation is. So what does g of x look like if it's negative f of x? We're just talking about the function negative square root of x, right? And what are we talking about here? We're talking about the square root of negative x, and here we're talking about negative the square root of negative x. And so if you were unclear on how I got these answers, you could just do a table of values on each of these and see what happens, and it'll be what we showed here. All right, let's keep moving. All right, parent function, just to summarize that, If you have the opposite of x inside, right, if you're inputting the opposite of x, that is going to be reflection across what? Across the y-axis. Okay, so that's going to flip it like a parabola. If you have the opposite, negative f of x, then that's going to be reflective across the x-axis. All right. Now, we didn't really talk about this because I'm hoping that you remember what happens with all the other, the adds, the subtracts. So I'm not reviewing that. Hopefully that won't be a mistake. Come see me if you're confused. So this first one, I'm hoping very much that we recognize the parent function because of the squared. And then we recognize that when it's x minus 5, we're going to move it over in the positive direction 5, and then we're going to go down 3. So to graph this, we should just go over to 5. 1, 2, 3, 4, 5, down 3. So my parabola, which was going to start here, is now going to start here, but the pattern stays the same. Up 1, up 3, up 5. Both directions. And this is our graph. 100% accurate. These points are perfect. But if you don't like a shortcut, what are you going to do? If you forget what's going on, pick your x's, solve for your y's. Okay, so now we've got the same idea, but now I'm going to, like what we just practiced, like what is this negative going to do? And so let's write all the transformations this is going to be. So I see 3 things. I see that we're going to shift 1 left. I see we're going to shift up 2. And then we're going to reflect. Now, here's the issue. If I now say reflect over the x-axis, I have not described this properly. And let's think about why. If I do it in the order of which I've just listed, then I'm saying take this square root graph, right, and move it to the left 1 and up 2. So it's going to be now sitting right here. And now if I reflect it over the y-axis, that means that I'm going to take it and it's going to come down here and do this. And that is not at all what I mean. Because what I meant to say or draw is it should be right there. So what is going to save us so that we don't get this wrong? When should we do our reflections if we're going to describe it? And the answer would be, depends on the reflection. But to be safe, if you always talk about your reflections first, I think you're always going to avoid that issue. Okay, so now let's try it. Now it's saying take your basic parent function, reflect it over the x-axis. Now it's here. Now shift the whole thing over to the left 1 and up 2, and we're going to be sitting right there, which is where it should be. Okay. Now, if you are going to talk about reflecting last, then that's fine, but you're going to have to not say x-axis, and instead you're going to have to, in this case, say over the line x or y equals 2, because that's kind of where your new y-axis is after you've shifted up 2. But you can avoid the whole thing by talking about that earlier. All right. Now, if I'm doing it though, and I'm drawing it, I usually reflect last, right? So I go over to the left 1, I go up 2, and now instead of going up 1 over 1, I'm going to go down 1 over 1, and down 1 over 1, 2, 3, 1, 2, 3, 4, 5. And so my graph should look more like that. Okay? But technically, I did this first, and then either of these second. All right. Let's come back to, now, you know what? Let's just do it. Let's do part C. Now, all of our rules for shifting only work if our leading coefficient on the variable is positive. Everything else gets thrown out the window if we don't fix that. So this is a problem that we cannot just say it does this and this yet. So what am I going to do? I'm going to do a little bit of math. If I can't have a leading coefficient that's negative, then that just means I'm going to factor out a negative 1. So I'm going to factor out negative 1, leaving me with an x minus 3. Ooh, that's way too big. And then I have my minus 2 on the outside. Okay. Now, sometimes, depending on your function, I can do something with this negative 1. Like, for example, had this been like a squared problem, then I'd be sitting here with a negative 1 inside the squared, and negative 1 squared is positive 1. So I could simplify further. But since this is a square root and I cannot take the square root of negative 1, it has to stay right where it is. But that's okay, because we know what it means to have a negative in front of our function there on the inside. And that is a reflection over the y-axis. So what is this graph going to do? Because of this negative, it's going to reflect over the x-axis or y-axis. It's going to shift to the right 3, and it's going to move down 2. All right, let's take a look. So my normal parent function's here. I'm contending that it's going to reflect. So now we're going to look like this. And then we're going to move it over 3 and down 2. So I'm going to be like sitting right here with this graph right there. So let's get it accurate. And then we could do a test to make sure we're not, going down the wrong path. So I think we're going shifting over 3 and down 2. And then instead of going this way, I'm just going to go the opposite direction. So up 1 over 1, up 1 over 3, 1, 2, 3, 4 over 5. So I think the graph looks like this. So let's test it. This point right here, that should be the point negative 1, 0. So let's test it. Let's do f of negative 1, which would be the square root of negative 1 plus 3 subtract 2. So that's negative makes 1 plus 3 minus 2, square root of 4 minus 2, 2 minus 2, f of negative 1 is 0. Feeling pretty good that we got it right. All right, let's do part D. I got the same problem. I got a negative in front of that x, and it can't be there. So I'm going to cube root, factor the negative out, leaving me with an x minus 5. However, this time I can simplify further because this is just a negative 1, and I can take the cube root of negative 1. And what is the cube root of negative 1? It's negative 1. So I can take the negative out. So what does that mean? That means on this function, I don't have to do any reflections across this way, which is a little bit feels uncomfortable, at least it does to me. Instead, I can focus on reflecting it vertically instead. All right, so I think this graph is going to, let's make a list. 1, reflect over the x-axis, and 2, it's going to shift right 3. All right, but you'll notice if we just talk about the reflection, this is a cubic graph, which looks like this. And you will notice that if I talk about reflecting it over the x-axis, like what I'm saying we're going to do, then this part's going to go down and this part's going to go up, and I get a graph that looks like this. But if I had left the negative on the inside, then this side would have reflected over here and would have looked just like this red, and this would have reflected and looked just like this red, and it doesn't matter, right? But in general, if you can take a negative outside of the function, then you should attempt to do so. All right. So let's graph this thing. I'm going to find the new starting point. 1, 2, 3, 4, 5. So it's shifted here. It hasn't gone up or down. And then instead of going up 1 over 1, I'm going to go down 1 over 1. And I'm going to go up 1 on this side. And then I'm going to go over 7 because it's a cubic. So 1, 2, 3, 4, 5, 6, 7. And then 7 more this way out there someplace. Okay. Let's keep going. All right. A little worried about the length of this video, and now starting to worry about the length of time it's going to take to teach this in class. So we may skip forward on some of this and assume that we know what's up. So this time we are looking at the function x squared. So let's get that parent function on here. 1, 2, 3. 1, 2, 3. And now I'm asking to graph g of x in red, which is a fourth of f of x. So if I rewrite what that new equation would be, that would just be me saying it's 1/4 outside of the function, so it doesn't affect the squared. So it's just 1/4 of x squared. So hopefully it doesn't take much to see that it's going to simply be what x squared used to be, right? And that would be this picture in black. And now it's going to be a fourth as tall. The outputs are a fourth what they would have been. So instead of going over 1 up 1, over 1 up 3, 5, 7, now I'm going to go over 1 only up a fourth. And then I'm going to go over 1 and not up 3. I'm going to go up a fourth of that. Because what I'm doing is this 1/4 is affecting the vertical scale. So the easiest way for me is to know my pattern and then just multiply it by whatever the scale is. So I'm going to go up a fourth. I'm going to go up 3/4. I'm going to go up 5/4, 7/4. You get it. So over 1 up a fourth, over 1 up 3 more fourths. That should be right here. 5/4, which should be a fourth up here, right? And so what I end up getting is this parabola that has shrunk. The heights of this parabola are now a fourth of what they used to be. Now, some people are going to say this thing is wider, and it is, but since we're talking about a scale change to the vertical, right, the 1/4 affects the vertical, I think it's a better way to talk about it, if you're going to be like kind of more precise, is that it's a fourth as tall, right? The output here used to be 4, right? At 2, we were at 4. Now we're at 1, which is a fourth as tall instead of it being wider. Okay, so then that means for this one, which would be change color, 2x squared, where the 2 is outside of the squared, had nothing to do with the squared. Now we're going to take our 1357 and we're going to double it. So now we're going to go up 2, 6, 10, 14. And again, that should hopefully make sense because if we looked at the table of values, we already know what the outputs of f of x are. And this is just saying, hey, take those outputs and double them. And so instead of going over 1 up 1, I'm going to go over 1 up 2. Then I would normally go up 3. Now I'm going to go up 6 instead. So 1, 2, 3, 4, 5, 6. So I'm up here. kind of faking this right now because I didn't make my graph big enough. And again, you might consider this a skinnier graph, but it'd be better to think of it as a taller graph. My output here was 1 right there, but now it's been doubled to 2. My output was going to be at 2, 4. Now it's going to be at 2, 8, doubled. All right, and then negative a half, that hopefully we know is going to flip it over and half the amount. So I'm going to skip that. So what does this tell us? If our value for C, so our reflections, so we know about reflections, okay, vertical stretch and compression. So if we're multiplying by a C value, it's going to either stretch it or compress it. So it's going to stretch it when C is what? Hopefully you said greater than 1. Multiply by 1, nothing happens. Multiply bigger than 1, it's going to stretch. And if C is between 0 and 1, let me put the C here, and I guess I could use interval notation here, but I'm committed. If C is less than 1, but greater than 0, let's try that again, greater than 0, then what we're going to do is we're going to get a shrinking, a vertical compression. It won't be as tall, in other words. Okay, so now let's just practice graphing a few and make sure we can get this all right. So let's make a list of what's happening. It is reflecting over the x-axis. It is 3 times, so stretching. Stretch 3 times. So that's a vertical stretch. And then our shifts. Shift, what, left 4 and up 7. All right, so our typical parabola, I wrote it this way, but I'm gonna think it another way. So I'm gonna move it first. So I'm gonna go to negative 4, 1, 2, 3, 4, and up 7. 1, 2, 3, 4, 5, 6, 7. So right about here. And now, instead of going up, I know I'm going down. And instead of my typical pattern of 1, 3, 5, I am tripling it. So 1, 3, 5 becomes 3, 9, 15. So I'm going to go down, over 1 and down 3. 1, 2, 3. And then I'm going to go over 1 and down 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Obviously, I'm not going to go beyond that. And if you want to test this, it's really easy. Did we do it right? Pick a known point and plug it in. Don't pick the origin, right? Don't pick the vertex, I mean. Let's pick something like this. What is this? 1, 2, 3, 4, 5, 6. This is negative 6. 1, 2, 3, 4, 5. So I think we have negative 6, negative 5. If we plug in negative 6, we should find out if we get negative 5. Let's do it. Do it in our heads. Negative 6 plus 4 is negative 2. Negative 2 squared is 4. 4 times negative 3 is negative 12. Plus 7 is negative 5. That's what we said it was. Part B, we've got our square root function, our radical graph here. But it is not shifting 18, number 1. That's a big clue. I'm not going to have you shift over 18. That's silly. But the issue is we have a 9 here. Now, we have to be careful. The common error on this is you're just going to take the 9 all the way out. A lot of kids are going to write this. Ooh, let's factor the 9 out, and we get x plus 2. That's almost correct. But you factored the 9 out, but you haven't taken the square root yet. So when I factor that 9 out, it's still under the square root. Now, if possible, apply the function to the number. And in this case, I can, because I can take the square roots of factors separately. And the square root of 9 is 3. And so I'm going to simplify this simply to this graph right here, which, listing the transformations, it's going to be a vertical stretch by 3 times as tall. And it's going to shift left 2. So I'm going to move it to the right place first, and that would be left 2. So it's just going to be sitting right here, didn't move up. But now my vertical pattern has changed. Now be careful. This is a square root graph. The square root graph is up 1 over 1, up 1 over 3, up 1 over 5. Notice always up 1. So now when I vertically stretch it, I'm changing my 1s to 3s. So it's up 3 over 1, up 3 over 3. It is not a horizontal scale change, it is vertical. And that is a common mistake that kids will make. They'll either do both or they'll just do it to the horizontal. All right, and this last, is it the last? Maybe it's not the last. Here we go. Same thing, the 2 in front messes it all up. So we're going to factor that 2 out, but be careful. That 2 that you factored out is just factored out of 2x minus 6. It is not factored out of the squared. Now the question is, can I square these two things individually? And the answer is yes. Our rule allows for that. And so 2 squared becomes 4. And it becomes 4 times x minus 3 squared minus 8. So what's it going to do? It's going to be vertical stretch, vertical scale change by 4. 4 times as tall, shifting 2 ways. Shift right 3 and down 8. I'm going to think about it in the moving first. So I'm going to go right 3 and down 8. 1, 2, 3, 4, 5, 6, 7. So we're down here someplace. We're going to fake this. And 4 times as tall. So over 1 up 4, over 1 up 12. So I've got a 4 and a 12. And I am full on faking this one because I honestly get a little tired. And that graph was a little big. All right. Oh my gosh, we're still not done. Here we go. Absolute value graph. So I don't like that -5 in the front. I'm going to move it to the back. That's no big deal. That's just style. But I do need to factor out that -2 in front of the x. So once again, I'm going to be careful. I still have that -2 inside the absolute value, but it's going to become now an x minus 4. I've got the -5 sitting out here. Right? So double check your math and distribute the -2 back in, and we should get where we started. Now, can we take the square root of -2? Square root, excuse me. Can we take the absolute value of -2? And yes, we can. It's 2. And then we're left with this absolute value of x minus 4 minus 5. So this is a v that's shifting over to positive 4, down 5. 1, 2, 3, 4, 5. And then my v, instead of being slopes of 1, are now going to be slopes of 2. And there we go. All right, let me take a look at example 5. We might just skip it for this video. All right. Yeah, I'm going to go ahead and probably end up skipping this in class. I'm worried about time. I was hoping to do all of this in one day. I'll finish this video, but we may end up skipping this one in class. Okay. Just because we've gone pretty long in this video. So rules don't work because I have a 1/2 there. So I need to deal with that 1/2. So I've got g of x equals, and honestly, I'm going to just put the negative parenthesis, and then I factor a 1/2 out, still inside the squared. That's going to be x plus 12. Because I'm dividing by 1/2 to figure out what to factor it out. And so dividing by half is the same as multiplying by 2. And so 6 turns into 12. You don't feel confident about it, just go ahead and distribute whatever you think it is back in and see if you get the same answer. You'll notice I just moved the plus 4 to the back. Once again, I can square each term individually, each factor individually, the negatives on the outside. So this becomes negative 1/4 x plus 12 squared plus 4. And now I know what's going on. I'm going to move all the way to negative 12 and up 4. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I'm going to go up 4. 1, 2, 3, 4. So this should be the point negative 12, 4. Now I'm going to go upside down and a fourth of what I normally would. So I'm going to go over 1, down only a fourth. I'm going to go down 3/4. I'm going to go down 5/4, which would be 1 1/4. And match it over here. And then I'll sketch this graph in. Vertex is here. So where is it increasing? It is increasing on the x values that are in the region negative infinity all the way to negative 12. It's going to decrease on all the x's from negative 12 to infinity. It is constant, never. And g of x is greater than or equal to 0. So what is that asking? That is saying, when is g of x bigger than 0? And that's going to be whenever it's positive. So I sort of gave up on so this is going to be down 7/4, which if I keep going, this was down, right? If I take my 1, 3, 5, 7 and multiply it all by a fourth, then I went down 1/4, 3/4, 5/4, 7/4. Well, it just so happens this was at a fourth down. So 7/4, I'm going to go down 3 more and then 4 more for 7. So I'm actually going to hit that point right there. And I'm going to be hitting that point right there. So when is it going to be positive? Oh, greater than or equal to 0. So it is 0. This is 12, 13, 14, 15, 16. So this is 16, 0. And this is going to be 1, 2, 3, 4, 5, 6, 7, 8, 0. Oh, negatives on both. Okay, so it is positive from negative 16 for the x's in the region, including, because it's or equal, negative 16 to negative 8. All right, did I ask anything else? Oh, when is it less than 0? So that's going to be on all the x's that are in the region from negative infinity to, where did it change? Negative 16, union, negative 8 to infinity. Okay, this was a long video, and I know it's a long video because my voice is tired, and hopefully this all made sense. You can go ahead and watch it again or ask questions in class if you need some support.